November 12, 1937. A test pilot wrestled with his aircraft, its wings shuddering violently as speed bled away. Below, the ground rushed up, a stark reminder of the unforgiving nature of early flight. This moment of impending disaster, a stall, was a common killer, yet one engineer believed he held a radical solution that could redefine aviation safety forever. To understand how it happened, we must go back to the nascent years of aviation, a time when the marvel of flight was inextricably linked with profound danger and uncertainty. From the very first powered flights by the Wright brothers at Kitty Hawk, the inherent instability of aircraft, particularly at low speeds and high angles of attack, presented a formidable and often deadly challenge. The aerodynamic stall, a phenomenon where the airflow separates from the wing's upper surface, leading to a sudden and dramatic loss of lift, was poorly understood by many and frequently catastrophic. Early aviators, often pioneers driven by an insatiable curiosity and courage, faced a constant battle against this invisible enemy. Their machines, while capable of brief and exhilarating flights, were prone to unpredictable behavior, especially during the critical phases of takeoff and landing, where precise control and sufficient lift were paramount. The statistics from this era were grim. A staggering percentage of early aviation accidents, encompassing both civilian and military operations, were directly attributable to stalls. These incidents claimed countless lives, often those of highly skilled and experienced pilots, and significantly hindered the rapid development and public acceptance of aircraft technology. The very act of flying was, for many, a testament to sheer bravery, but also a high-stakes gamble against the fundamental physics of the air. Engineers and designers across the globe grappled with this pervasive problem, seeking ways to make flight more forgiving, more accessible, and ultimately safer for all who dared to venture into the skies. The quest for a reliable solution to the stall was not merely an academic exercise. It was a matter of life and death shaping the very future of aviation. The specific situation in the decades leading up to World War II further highlighted this urgent and growing need for innovation in stall prevention. As aircraft design rapidly evolved from the fragile biplanes of the Great War to the more robust, faster, and heavier monoplanes of the 1930s, their performance capabilities increased dramatically. However, the fundamental issue of stall characteristics remained a persistent and deadly threat. Military strategists, envisioning vast air fleets that could project power across continents, understood that the high accident rate due to stalls was a significant impediment. Training new pilots was an incredibly costly and dangerous endeavor, often resulting in the loss of valuable airmen and expensive machines before they ever had the chance to see combat. This attrition rate was unsustainable for any large-scale military expansion. Commercial aviation, too, struggled to gain widespread public trust and acceptance when every flight, particularly during the critical phases of approach and departure, carried the implicit risk of an unrecoverable stall. Existing solutions, such as rudimentary leading-edge slots or minor trailing-edge flap adjustments, offered only incremental improvements. While they might slightly reduce the stall speed or provide a brief warning, they failed to address the core problem comprehensively, often introducing other complexities or limitations. Pilots were rigorously taught to recognize the subtle warning signs of an impending stall, the characteristic buffeting, the mushy controls, the loss of control authority, but in high-stress situations, such as combat maneuvers or emergency landings, or with less experienced hands at the controls, these warnings often came too late for effective recovery. The demand for aircraft that could operate safely across a wider range of speeds, particularly at the lower end, required for safe landings and short takeoffs, was immense and growing. This was not merely about convenience or efficiency, it was about the very viability of aviation as a transformative force, both in times of peace and during the looming global conflict. The stage was unequivocally set for a truly revolutionary idea, one that would challenge conventional aerodynamic wisdom and fundamentally alter how aircraft wings interacted with the air, offering a new paradigm for flight safety. Into this challenging and high-stakes environment stepped Edward Zaparka, an engineer whose name would eventually become synonymous with a radical and effective solution to the pervasive stall problem. Born in 1894, Zaparka possessed an exceptionally inquisitive mind and a deep, almost innate fascination with the intricate mechanics of flight. From a remarkably young age, he exhibited a keen interest in how things worked, often spending countless hours tinkering with models, dissecting mechanical devices, and meticulously sketching his own innovative designs. His early life was marked by a relentless and self-driven pursuit of knowledge, fueled by an intrinsic desire to understand, and more importantly, to improve the world around him. Zaparka was not content with merely accepting established norms or conventional wisdom. Instead, he constantly questioned existing paradigms, seeking alternative approaches and challenging assumptions that others took for granted. This innate curiosity, combined with a meticulous attention to detail and a methodical approach to problem-solving, would prove to be the bedrock of his future, groundbreaking innovations. Zaparka's early experiences, both academic and practical, instilled in him a profoundly pragmatic approach to engineering, one that consistently prioritized functional effectiveness and real-world applicability over theoretical elegance or abstract concepts. He understood implicitly that, especially when human lives were at stake, a solution's practical utility far outweighed its intellectual sophistication. His journey into aviation was not merely a career choice or a professional path. It was, for him, a profound calling, deeply fueled by the ambitious and noble goal of conquering one of flight's most dangerous and persistent adversaries, the aerodynamic stall, which had claimed so many lives and stifled so much progress. Edward Zaparka's formal education provided him with a strong and comprehensive foundation for his unconventional and innovative thinking. He pursued rigorous engineering studies, immersing himself deeply in the complex principles of mechanics, the fundamental laws of physics, and, crucially, the then-emerging science of aerodynamics. Unlike many of his contemporaries in the early aviation field, who often focused primarily on maximizing aircraft speed or engine power, Zaparka developed a particular and specialized interest in the more subtle and intricate aspects of airflow dynamics and lift generation. He recognized early on that the wing, the very component responsible for generating the lift necessary for flight, was also paradoxically the primary culprit in the phenomenon of stalls. After successfully completing his academic studies, Zaparka embarked on a professional career that saw him working with various pioneering aircraft manufacturers. This period provided him with invaluable practical experience, allowing him to observe and analyze real-world aviation challenges firsthand. He spent countless hours observing aircraft in flight, meticulously analyzing accident reports that detailed the tragic consequences of stalls, and poring over nascent wind tunnel data, which offered glimpses into the invisible world of airflow. These cumulative experiences reinforced his growing conviction that a fundamental and radical change was needed in wing design, rather than just a series of incremental tweaks or minor modifications. He clearly saw the inherent limitations of existing flap systems, which, while capable of increasing lift to some extent, often did so at the expense of increased drag and, more importantly, did little to fundamentally alter the wing's critical stall characteristics or improve low-speed control. His previous experiences, particularly his first-hand observations of numerous stall-related accidents and the detailed analysis of their causes, fueled an unyielding determination within him. Zaparka witnessed, with a profound sense of urgency, the devastating consequences of an aircraft losing lift unexpectedly and uncontrollably. He understood, perhaps more deeply than many, the sheer terror experienced by a pilot losing all control, the machine tumbling helplessly from the sky, often with fatal results. These vivid and tragic images solidified his resolve to find a truly effective and comprehensive solution to the stall problem. Driven by this powerful motivation, he began to experiment with various conceptual designs, often sketching ideas that seemed outlandish, even revolutionary, to his more conservative peers. He explored innovative ideas for actively altering the wing's camber and overall area in ways that went far beyond the simple, hinged trailing edge flaps then in common use. Many of his early proposals were met with significant skepticism and sometimes even outright ridicule from established engineers who believed that the fundamental limits of wing design had largely been reached and that radical changes were unnecessary or impractical. They often dismissed his ideas as overly complex, mechanically unfeasible, or simply too radical to be effective. Yet Zaparka remained completely undeterred, driven by an unwavering belief that a genuine breakthrough was not only possible but imperative, if only one dared to think boldly and outside the established paradigms of aeronautical engineering. He knew with absolute certainty that the problem of the stall was not merely a complex technical challenge, it was, at its core, a profound human one, directly affecting the lives of countless pilots and shaping the very future and public perception of aviation. The critical insight that would eventually lead to his revolutionary design began to crystallize during a period of intense personal study, meticulous observation, and relentless experimentation. Zaparka realized that simply increasing the wing's curvature, or its overall surface area, was not in itself a sufficient solution. The true key, he theorized, lay in actively controlling the delicate airflow over the wing's upper surface, particularly at the high angles of attack where stalls typically occurred. He envisioned a flap system that would not only extend downwards, as conventional flaps did, but would also simultaneously slide rearwards. This dual movement would effectively increase the wing's chord, its front-to-back dimension, and its overall surface area, while crucially creating a precisely engineered slot between the main wing and the extended flap. This slot, he hypothesized, would allow high-pressure air from beneath the wing to flow over the upper surface of the flap, thereby re-energizing the boundary layer, the thin layer of air directly adjacent to the wing's surface. By doing so, it would significantly delay the onset of flow separation, which is the very aerodynamic phenomenon that causes a stall. This was a truly radical departure from conventional flap designs and the prevailing aerodynamic thinking of the era. It was a moment of profound clarity, a sudden and comprehensive understanding of how to manipulate the air in a dynamic and controlled way that would fundamentally alter the wing's behavior at low speeds. This crazy idea, as some initially perceived it due to its complexity and novelty, was born not from mere speculation, but from a deep, intuitive understanding of aerodynamics and an unwavering commitment to solving a problem that had plagued aviation since its very inception. It was a concept that promised to transform the aircraft wing from a relatively static lifting surface into a dynamic, adaptable, and highly controllable component, capable of maintaining lift and control even when conventional wings would have long since given up their fight against gravity. The prevailing aerodynamic theories of the time, while certainly advanced for their era, often favored simplicity of design and structural integrity above all else, especially when it came to high-lift devices. Engineers were generally wary of introducing intricate mechanical systems into aircraft wings, fearing that such complexity would inevitably lead to increased weight, introduce significant maintenance issues, and create potential points of structural failure in a highly stressed environment. Zaparka's concept, which involved a flap that not only deflected downwards but also translated rearward along a track, was viewed as a significant and audacious departure from these established rules of aircraft design. The skepticism he faced from many within the aviation community was considerable and often vocal. Critics argued vehemently that the mechanical complexity required for such a system would be prohibitively high, making it unreliable and difficult to manufacture. They also pointed to the potential for a significant weight penalty, which was a critical concern in aircraft design, and questioned whether the promised aerodynamic benefits would truly outweigh these drawbacks. Furthermore, many doubted the reliability and durability of such an intricate mechanism operating under the extreme stresses and vibrations inherent in flight. The dilemma for the aviation industry was clear: continue to adhere to proven, albeit limited, designs that offered incremental safety improvements, or embrace a radical, unproven concept that promised unprecedented and transformative advancements in flight safety. Zaparka, however, possessed a deep understanding that true progress and revolutionary breakthroughs often required challenging the deeply ingrained status quo and venturing into uncharted territory. He firmly believed that the potential benefits of his design, particularly in terms of saving lives and expanding the operational envelope of aircraft, far outweighed the perceived risks and engineering challenges. He was prepared to fight tirelessly for his vision, convinced that the rules of aviation design needed to be fundamentally rewritten if the industry was to overcome its most persistent, dangerous, and costly challenge. Despite the initial and often intense resistance from conservative elements within the aviation industry, Zaparka's unwavering conviction and persistent advocacy for his design eventually led to a critical moment of decision that would alter the course of aviation history. He managed to secure crucial support from a forward-thinking aircraft company, the Zap Development Corporation, which, despite the prevailing skepticism, recognized the immense potential and transformative power of his revolutionary design. This was a pivotal and courageous step, as it provided Zaparka with the necessary resources, financial backing, and most importantly, the platform to move his groundbreaking idea from mere theoretical sketches and conceptual drawings to a tangible, working prototype. The decision by the Zap Development Corporation to invest heavily in such an unconventional and unproven design was a remarkably bold one, reflecting a rare willingness to gamble on true innovation and to challenge the deeply entrenched norms of the industry. With the critical funding and institutional support secured, Zaparka and his dedicated team of engineers and technicians embarked on the arduous and meticulous process of translating his visionary concept into a functional and flight-worthy model. This monumental undertaking involved countless hours of detailed design work, intricate mechanical engineering, rigorous stress analysis to ensure structural integrity, and extensive wind tunnel testing to validate the aerodynamic principles. Each step of this complex development process was met with new and unforeseen challenges, requiring ingenious solutions to both mechanical and aerodynamic problems that had never been encountered before. The crazy idea, once dismissed by many as impractical, was slowly but surely taking concrete shape, moving ever closer to its ultimate and most critical test, actual flight. This period was a profound testament to Zaparka's extraordinary perseverance, his unshakable belief in his vision, and the courage of those few individuals who dared to believe in and support his revolutionary approach to wing design, understanding that true progress often demands a leap of faith. The development and subsequent testing of what became famously known as the Zap Flap was a meticulous and painstaking process, characterized by rigorous engineering and relentless refinement. Unlike conventional flaps that simply hinge downwards from the trailing edge of the wing, Zaparka's ingenious design incorporated a sophisticated track and roller mechanism. This allowed the flap to execute a complex dual movement. It would not only extend downwards, increasing the wing's curvature, but also simultaneously slide rearwards. This combined movement had a profound aerodynamic effect, significantly increasing the wing's chord, its front-to-back dimension, and its overall surface area. The result was effectively a larger, more curved wing surface available at low speeds, dramatically enhancing lift. Crucially, as the Zap Flap extended, it also created a precisely engineered slot between the main wing and the deployed flap. This slot was the key to its revolutionary performance. It allowed high-pressure air from beneath the wing to flow through the gap and over the upper surface of the extended flap. This directed flow of air served to re-energize the boundary layer, the thin layer of air directly adjacent to the wing's surface, thereby significantly delaying the onset of flow separation, which is the primary cause of an aerodynamic stall. The net effect was a dramatic increase in maximum lift and a much higher stall angle, meaning the aircraft could fly safely and maintain control at significantly lower airspeeds than previously possible without losing lift. Initial wind tunnel tests provided compelling and undeniable evidence of the Zap Flap's effectiveness, consistently showing a remarkable improvement in lift coefficients and a far more benign stall characteristic. These highly promising results quickly led to the construction of a full-scale prototype aircraft specifically equipped with the revolutionary Zap Flap system. Test flights commenced, cautiously at first, then with increasing confidence and enthusiasm as experienced test pilots experienced firsthand the unprecedented control and stability the aircraft exhibited at low airspeeds. The detailed action involved countless adjustments, meticulous fine-tuning of the flap's extension angles, and continuous refinement of its mechanical mechanisms, all to ensure its utmost reliability and smooth operation under a wide range of flight conditions. Engineers meticulously collected vast amounts of data, rigorously comparing the Zap Flap's performance against conventional flap designs, and the numbers consistently demonstrated its superior ability to mitigate the dangers of stalling. The immediate result was unequivocally clear. The Zap Flap worked, and it worked exceptionally well. It fundamentally transformed the handling characteristics of the test aircraft, making it far more forgiving, controllable, and predictable at speeds that would have previously led to a dangerous and potentially fatal stall. The promise of a safer future for aviation was no longer a distant theoretical concept, but a tangible and proven reality, demonstrated convincingly in the unforgiving environment of actual flight. The successful demonstration of the Zap Flap's capabilities quickly sent ripples of excitement and interest throughout the global aviation community. Its widespread adoption was not immediate or universally instantaneous, as is often the case with truly revolutionary technologies, but its profound and undeniable impact on aircraft safety and performance, particularly during the critical and accident-prone phases of takeoff and landing, became increasingly evident. While the claim of stopping 90% of stall crashes is a dramatic and perhaps hyperbolic way to emphasize its significance, the Zap Flap, and more importantly, the fundamental aerodynamic principles it introduced, undeniably led to a substantial and measurable reduction in stall-related accidents across various aircraft types. Its ability to allow aircraft to fly slower, with greater control authority, and at significantly higher angles of attack was an invaluable advancement. This was especially true as aircraft designs became progressively heavier, faster, and more complex, making low-speed handling and stall recovery an increasingly challenging and critical aspect of flight safety. The innovative design principles embodied in the Zap Flap directly influenced the development of subsequent generations of high-lift devices, most notably the Fowler flaps, which also extend rearward to increase wing area and incorporate slot effects. During the tumultuous years of World War II, the urgent need for robust, forgiving, and highly maneuverable aircraft was paramount. Fighters and bombers often had to operate from rudimentary, battle-damaged airfields, execute tight and demanding combat maneuvers under extreme stress, and land under adverse weather conditions, or after sustaining battle damage. Aircraft designs incorporating advanced high-lift systems, directly inspired by or even directly utilizing Zaparka's groundbreaking concepts, provided pilots with a crucial and often life-saving margin of safety. This not only reduced costly training accidents, preserving valuable resources and personnel, but also significantly improved the operational effectiveness and survivability of combat aircraft. The repercussion of Zaparka's work was a fundamental and lasting shift in how aircraft designers approached wing design, prioritizing not just the pursuit of maximum speed or range, but also placing equal importance on low-speed controllability, enhanced lift, and robust stall resistance. His work helped usher in an era where safety was integrated into the core design philosophy rather than being an afterthought. The historical impact of Edward Zaparka's crazy wing flap design was truly far-reaching and transformative, fundamentally altering the trajectory of aviation safety and performance for generations to come. His innovation helped to rewrite the rules of flight, demonstrating conclusively that aircraft wings could be dynamic, adaptable surfaces, capable of actively manipulating airflow rather than merely static, fixed structures. The concept of extending and slotting flaps, pioneered by Zaparka, became an indispensable cornerstone of modern aerodynamic design, integrated into virtually every commercial airliner, military transport, and high-performance aircraft built since. This wasn't merely about preventing crashes, although that alone was a monumental achievement. It was about enabling entirely new possibilities for aviation. Safer takeoffs and landings, meant that significantly larger, heavier, and more complex aircraft could be developed and operated with confidence, thereby expanding the reach and efficiency of both commercial air travel and critical military logistics. Pilots, no longer constantly battling the ever-present threat of an unexpected stall, could focus more effectively on navigation, complex combat maneuvers, or ensuring passenger comfort and safety. Zaparka's pioneering work laid the essential groundwork for the sophisticated multi-slotted, multi-segment high-lift systems seen on today's massive airliners, which allow these colossal aircraft to take off and land at remarkably low speeds, defying their immense weight. His contribution underscored with undeniable clarity the profound importance of challenging conventional wisdom, embracing radical ideas, and pursuing innovative solutions in the relentless pursuit of safety and technological progress. It transformed the very perception of what an aircraft wing could achieve, moving beyond simple lift generation to active and intelligent control of airflow, thereby making the skies a far safer and more accessible place for countless generations of aviators and travelers. After his groundbreaking and revolutionary work on the Zap Flap, Edward Zaparka continued to contribute significantly to the field of aviation, though perhaps not always with the same dramatic public recognition that accompanied his initial breakthrough. His legacy, however, was firmly and irrevocably established in the fundamental aerodynamic principles he introduced and the design philosophy he championed. He continued to work diligently as an engineer and innovator, applying his keen intellect and problem-solving acumen to various complex challenges within the rapidly evolving aerospace industry. While the specific details of his later life and subsequent projects are less widely publicized than the initial transformative breakthrough of the Zap Flap, his profound influence persisted and permeated through the widespread adoption and continuous evolution of his core design principles. He lived to witness his once crazy idea become not just accepted, but an indispensable standard practice across the entire aviation world, undoubtedly saving countless lives and enabling the incredible exponential growth of aviation as a global force. Zaparka passed away in 1989, having had the immense satisfaction of witnessing the complete transformation of flight from a perilous and uncertain adventure into a remarkably routine and safe mode of transport, a monumental transformation to which his ingenuity, perseverance, and vision had made an indelible and lasting contribution. Edward Zaparka's crazy wing flap design stands as a powerful and enduring testament to the profound impact of visionary engineering and the courage to challenge the status quo. It reminds us with compelling clarity that true progress and revolutionary advancements often emerge from those individuals who are willing to question established norms, to push the very boundaries of what is considered technically possible, and to persevere with unwavering determination in the face of skepticism and resistance. His innovation didn't merely add a new, albeit complex component to an aircraft, it fundamentally and irrevocably changed the intrinsic relationship between an aircraft wing and the air it moves through, making flight inherently safer, significantly more reliable, and ultimately far more accessible to humanity. The countless lives saved, the pilots who returned safely home from their missions, and the millions of passengers who have traveled securely across vast distances all owe an immeasurable debt to the engineer who dared to dream of a wing that simply wouldn't give up. This is the true and lasting legacy of Edward Zaparka, irrefutable proof that a single brilliant idea, born from a deep understanding of fundamental principles and a relentless pursuit of safety, can indeed change the world, one flight at a time, one life at a time.